Okay, so we've been talking about how to use law of sines and law of cosines to solve for missing sides of triangles, but we're going to start talking about a way to solve for angles instead of sides. So if we're looking at this basic right triangle, we have theta, our angle in the corner, and then we have the adjacent side and the hypotenuse. So normally we would say, okay, well then the cosine ratio of angle theta is equal to adjacent over hypotenuse, so that's 3/16. But we want to have a way to solve for the angle theta, so we want to be able to know what angle would create that ratio of 3/16. So today we're going to work on finding a method for that. So what we're going to do is we're going to look at our cosine function first. So as we learned in the past unit, the cosine function is an oscillating wave, so it oscillates back and forth from 1 to -1, and its domain is the all real numbers. So we have our domain is all real numbers, and our range goes from our minimum of -1 up to our max of +1. So we want to restrict the domain of this function somehow to create an inverse function. So inverse functions, which we've learned about, is you switch the domain and range. But if we were to switch the domain and range of this function, we would get a wave that would just be going up the y-axis instead, and that wouldn't constitute a function. So we want to restrict the domain in order to create a function. So when we restrict the domain, we want to include a few different criteria. So we're going to figure out how we want to look at this graph, which section of the graph we need to look at for our inverse function. So there are three things that we need to consider. The first thing is that our domain should include the angles between 0 and pi/2. Because those are all of our acute angles. So those are all of the acute angles that would occur in a triangle. We also, on the restricted domain, want to have all of the values, so have all values represented. So that means all of our y values between 1 and -1. Whoops, spelled that wrong. And then the third thing that we want to consider is that our domain needs to be continuous. So we want to come up with a restricted domain of the cosine function that meets all three of those criteria. Okay, well the first one is easy. We need to include from 0, so here's our 0 point, so we'll go to 0 on the curve and include to pi/2. So we have to include this section of the curve. Our second thing says that we have to have all values represented. So we have all of the positive values of cosine, everything above the x-axis. So we now also need to include all the negative values. And we also need our domain to be continuous, which means I can't just hop anywhere I want. So in order to make it continuous, I either have to go somewhere from our endpoint at 0 or our endpoint at pi/2. Well, if I go to 0 and I go to the left, so if I were to go in this direction, I would just still have the positive values of the curve. So I can't do that. So that means I have to go this direction. So I'm going to go all the way down to pi, because if I stop at pi, that means I have used all of our values from -1 up to +1. So this little section of the cosine graph is going to be our restricted domain for creating the inverse function. So what that means, an inverse function is what we're going to talk about on the next page. We're going to define inverse cosine. So the definition of inverse cosine says that y is equal to cosine -1 of x if and only if x is equal to cosine of y and 0 is less than or equal to y, which is less than or equal to pi. So let's break this down, what all of this means. So this -1 symbol, that's our inverse. That's how we designate inverse functions, with the -1. So if we have our original function as x is equal to cosine of y, so that's our original. And if we want to solve for y, we would take the cosine of both sides. So to get the y angle that's trapped inside of the cosine function out, you take the inverse cosine of the other side, and that's equal to the angle. And this angle is going to be between 0 and pi, or 0 degrees and 180 degrees. So when you look at your graphing calculator, it has that inverse cosine function button. If you hit the second key and then the cosine key, you'll see it. Your answers that your calculator will give you are always going to come out between 0 and pi, or 0 degrees and 180 degrees, depending on the mode of your calculator. So over here on the left is our regular cosine function with its restricted domain, which is what we came up with on the other side. So 0 less than or equal to x less than or equal to pi. And then it has the same range. And what we've learned about inverse functions is the inverse switches the domain and range. So if we look over on the right-hand side of the screen at the inverse cosine, we see that the domain is from -1 to +1. So hang on, this is a typo from your textbook. So -1 is less than or equal to x, which is less than or equal to +1. So you can only plug in these types of values. To the inverse cosine function, and you're going to get out angles between these two values. So for inverse functions, you plug in the ratio, you plug in that adjacent over hypotenuse ratio or decimal value, and you get out the angle that would create it. So the first example we're going to look at is evaluating the inverse cosine of the square root of 3 over 2 without a calculator. And we want to give our exact answer in radians. So one way to think about this is that some cosine of some theta value is equal to root 3 over 2. So when we're solving for theta, that means we take the inverse cosine of root 3 over 2. Or another different notation that you might see, instead of the -1 exponent, you might see this. You might see the words arc cosine of root 3 over 2. So this is just another notation for inverse. So what they're asking us to do is they want to know what angle would give us a cosine ratio of root 3 over 2. And remember, our angles for cosine have to be between 0 and pi. So I have a unit circle up here on the board for us to look at, but normally you would have to have this memorized. So if you don't remember your unit circle values, you need to go back and relearn those. So for inverse cosine, we can only look between 0 and pi. So I'm going to just cross off the bottom half of the circle. So our answer has to come between somewhere from 0 around to pi. So remember, in our unit circle, cosine is the x value, sine is the y value. So we're looking for an x value that is positive root 3 over 2. So since cosine is positive, that's going to be somewhere in the first quadrant, because cosine is negative in the second quadrant. And we can see that at pi over 6, we have a cosine value of root 3 over 2. So the inverse cosine of root 3 over 2 has to equal pi over 6. So that's our final answer. For our second example with inverse cosine, we're going to go to our calculator. So we'll show you how to do that on our calculators. So if you look on your calculator screen, you're going to be able to see that you have a cosine button, and then if you hit the blue second key, you get the cosine inverse. So for your calculator, your steps are going to be to first check your mode. So this question is asking for our answer in degrees, so we want to first go to our calculator and check mode and make sure that we are on degrees. I'm already on degrees, so I'm good to go. And then your second thing is, in order to get the inverse cosine, you're going to hit the second button, and then the regular cosine key. So I'm going to do that. I'm going to type in cosine -1 of -0.33333. So we're going to go ahead and type that in. Hit enter, and we find that this is approximately equal to 109.47 degrees. So your calculator is always going to spit out the answer between 0 and 180 degrees or 0 and pi. And we're going to start talking about how to come up with additional solutions outside of that basic restricted range and domain of the inverse function. Okay, for our third example, we're going to look at an application of the inverse cosine function. So we're going to read through this together. The Landsat 7 satellite orbits Earth at an altitude of 705 kilometers, which is 438 miles above the equator. It can only see a portion of Earth's surface bounded by a horizon circle as shown below on the left at any given time. Imagine looking at a cross-section of the satellite and Earth as shown below on the right. Point C is the center of Earth. H is a point on the horizon circle, and S is the location of the satellite. You want to let theta be the measure of angle HCS, so they already have it labeled down here in the corner for us. The altitude A of the satellite is the distance in kilometers of the satellite above Earth. Notice that angle CHS is a right angle because it is a tangent line to the Earth. So because the tangent to a circle is perpendicular to the point of tangency. So first we want to write a formula for theta in terms of R and A. Okay, so if we're looking at theta here, we know that this side over here is our hypotenuse because it's across from the right angle, and then that R over here is our adjacent side. So we're perfectly set up for cosine. So if we're looking at section A, we would know that cosine of theta is equal to the adjacent side, which is R, over the hypotenuse. Well, if we're looking at the hypotenuse, we have this section here, which is R, the radius of the Earth, and we have this additional segment A. So our total hypotenuse is going to be the segment R plus A. So that's our cosine value, but we want to write a formula for theta. So when we say write a formula for theta, we want theta equals something. So if we want to just solve for theta, to get it outside of the cosine, we take the inverse cosine of the other side. So we move cosine to the other side and take the inverse. So we do cosine -1 of R over R plus A. So that would be our formula. So then we'll move on to part B. So we know that the radius of Earth is about 6,378 kilometers. So I'm going to go ahead and label that onto our picture. So we know R is 6,378 kilometers. 6,378 kilometers. And then we want to find to the nearest degree what theta is. So we know the altitude, or A, of our satellite is 705 kilometers. So we're going to put that on as A. So then we're just going to plug into our formula. So we know theta is equal to the inverse cosine of R, which was 6,378, over R plus A. So that's 6,378 plus our altitude value of 705. So I'm going to go ahead and combine our like terms in the bottom. So 6,378 plus 705 gives us a total of 7,083. So theta is now equal to the cosine inverse of 6,378 over 7,083. And now they want it to the nearest degree. So again, remember your calculator steps, check your mode, but we're already in degree mode from the last example. Then we hit second cosine to get our inverse cosine function, and then we just type what we see. So 6,378 divided by 7,083, close our parentheses, hit enter, and we get that theta is approximately 25.78 degrees. So that means that the angle between the satellite and the point of tangency of the Earth at point H is 25.78 degrees. Okay, so I want you to use those past three examples and the definitions we've gone over to answer numbers 5 through 9 from your textbook on page 302. I've also put the questions here in case you don't have your textbook at home, so you could pause the video and read them off the screen now.